I'm CJ. I'm going to talk to you about Axelar today and XRP Ledger integration. So yeah, this is a very technical. This is a very technical presentation. So if you have any questions, like feel free to raise your hand and stop me at any time. I'm happy to answer questions as I go. I don't want anyone to be confused. So, a little bit about myself. Yeah, I'm a software engineer at Interop Labs. We develop the Axelar network and all aspects of the stack. Before Axelar, I worked at Ripple for 4 years, so I'm pretty familiar with XRP Ledger, how it works. I was on the core team at Ripple, and I actually was the first developer of Project Clio, for anyone who knows about that. So what is Axelar? Axelar is a Web3 interoperability platform. At the center of it is a proof-of-stake blockchain. It's a Cosmos chain, and it's a layer 1. It's just a normal layer 1, and it acts as a hub between any connected chains. But there's more than just the blockchain itself. There's all kinds of layers of the stack and things that exist on the external chains that make it work. And what it does is it enables secure message passing between chains. So it's not just token bridging, but it's passing generic messages. And token bridging is just one of those messages, but it is greater than that, right? So you could do anything. Any two chains that are connected to the Axelar network can talk to each other, right? And so this is a hub and spoke model. So when you integrate with Axelar, you immediately get connections to all the other chains. We have over 60 chains today and many more in the pipeline, right? So like when XRP Ledger integrates with Axelar, you can send messages to Ethereum, to Polygon, to Avalanche, right? And we have, like Bitcoin coming, Solana coming, and immediately you'll be connected to those chains, right? So this is really powerful because a lot of bridges are just pairwise, and that doesn't really scale as much as a hub and spoke model, where you just eventually there'll be 100 chains, or every chain you could think of is connected through Axelar. So, okay, why cross-chain? Someone maybe put this slide in, but. So why does cross-chain matter? I actually run into this in my daily life. Like, I am a crypto native. I hold tokens on several chains. And I often want to swap them, but there is no route often outside of centralized exchanges. But centralized exchanges have problems, right? They charge high fees. Like, you have to give up custody of your tokens. Like, sometimes there's regulatory issues. So it's a problem, right? I've run into this problem on XRP. I'm an XRP holder and often can't move my XRP without finding an exchange. And when the SEC case was going on, that was really a problem because there weren't a lot of exchanges that would work with XRP in the US. So cross-chain solves this problem where you can retain custody of your tokens, like the whole time when you want to do a swap, move tokens around. You don't have to give up custody of your tokens on board on an exchange, all that. But you can also, let's say, execute a smart contract on a remote chain. So take the XRP Ledger example. Like, I can call a smart contract that's on Ethereum or on Polygon from XRP Ledger, from mainnet, without having a wallet or an account on Ethereum, right? And that smart contract can do some logic and then send me back tokens, right? And I never need to leave the chain that I like, that I'm on, that I set up my wallet for, but I can still use the other chains, right? So this is really powerful. All right. This clicker doesn't work very well. Okay, so today I'm going to talk to you about this thing called Interchain Amplifier, which is basically like version 2 of the Axelar protocol, the original Axelar protocol that's live on mainnet right now, mostly just bridges between EVM chains and Cosmos chains, right? But as Axelar grew, we wanted to make a protocol that was more generic, that could integrate with any type of chain, with any smart contract language, any consensus mechanism. It didn't matter. And it is also programmable, right? That you can change the way messages are verified, change the security, improve upon it as research is done in the community without having to stop the chain, hard fork. It's very modular. So that's what I'm going to talk about today. This is live on DevNet right now and is launching to mainnet this summer. But so if you go read docs after this, some docs, a lot of docs still refer to existing legacy deployment, but I'm going to talk to you about the new stuff today. All right, so for any interoperability platform, there's several key components, right? And different interoperability solutions call these different things, but these are sort of essential. And Axelar has these components. So the first component is called a relayer, right? And this is a permissionless component that is designed to pass messages from one chain to another. It doesn't necessarily it's not relied on for correctness, it just provides liveness. So blockchains can't talk to each other, and the relayer provides liveness. But everything the relayer passes needs to be verified, right? It's not just trusted. And that's where these things called verifiers come in. And these are generally off-chain entities that attest to the correctness of some cross-chain message, right? Like if the relayer passes a message, the verifiers check, is this correct? And they do something. In the typical example, they vote, they might do signing, doesn't matter. There's something in the middle that sort of secures the bridge. They secure the bridge, they're verifiers. In our architecture, they are selected via proof of stake and also a governance vote. Then there's the external gateway, which is the entry point to the protocol that exists on external chains. So on every chain connected to Axelar, there's some smart contract or some mechanism, something that users and dApps talk to send messages across the Axelar network, and that's also how they receive messages. So it's the entry point on the external chains. And then we have a bunch of smart contracts on Axelar itself that are responsible for routing, understanding where a message should go, making sure messages are verified, they're in the right format, all that stuff. So this is the gateway API. This is the external gateway API. This is how people interact with the Axelar network. This is how you send messages. So on the left side here, we have sending. This is Solidity, by the way, so EVM land. So you have sending. So when you want to send a message, you just specify where, right? What chain, what contract on that chain, and then the payload, which is what you want to send, right? And this could be arbitrary data. It's just bytes. It could be very, very large. It could be small. It could be medium. Doesn't matter. If it has structure, if you want to send structured data, you serialize that to bytes. And then on the other side, when you receive it, so this is the receiving interface, you deserialize that payload and turn it back into your structure, right? So basically the way it works is apps deploy on the chains that they want to work on, and they're sending messages to themselves, right? So when a message is sent, eventually the app receives the message on the other side, and it gets, the source chain, where it came from, source chain, source address, and the same payload. And this is all verified, right? Once the app receives this, it knows this was verified, this was correct, this was sent, and this was sent only once, right? There's no so you can't replay attack. So this is the message flow through the whole protocol. I abstracted away a lot of things to make it look simple. But basically, you have your source chain on the left, the dApp talks to the gateway, the relayer hears that happen, picks up the event, turns it into a message, and we have a standard message format, the packets are the same structure, no matter what chain it is. Sometimes there's a translation that has to be done, but picks up the packet, passes it to the Axelar network. Every connected chain has some associated contracts on the Axelar network that secure that chain. They define how messages are verified on that chain, if there's a translation that needs to happen, etc. And they plug into this one contract that is really the heart of the protocol. It's called the router, right? And the router is where we write. I've worked a lot on the router. And that's the heart of the protocol, and that's how messages are passed between different chains, right? So the router accepts these messages from the gateway once they've been verified, and then passes them to another set of contracts that are associated with the destination chain, still on Axelar. Those contracts do some things, some transformation, get it ready, and the relayer then takes the messages and passes them to the destination chain, through the gateway and eventually the dApp. So this is the flow. So the relayer is not trusted. That could be anyone. If the relayer goes down, you could be the relayer. You can manually relay your transactions. Not trusted at all, right? But the other things, the smart contracts, they're obviously trusted in the sense that smart contracts are. So yeah, that's how that works. Any questions? Yes?
So mainly, what is the incentive or the payment flow here, and how is that charged back or forward across the networks?
How do tokens move?
No, is there a fraction of a payment, some sort of a fee or gas fee for crossing the Axelar network?
Gas, yeah. So that's a good question. I'm not going to talk about that. I didn't put that in this presentation, but I will answer the question. So yeah, this costs gas, across this whole stack. That part is not part of the protocol, right? And it's basically the people paying the gas are the relayers, right? And the relayers are these off-chain components. So basically, when you make a message call, you pay gas to the relayer. So on the source chain, the user pays gas in their native token of that chain to the relayer, and the relayer makes sure it gets all the way through the protocol. That's like a whole thing, like understanding like how much gas do I need to pay for this arbitrary message execution. But yeah, it's handled at the relayer level, basically like up here. It's a good question though. But from the point of view of the protocol, that's not, like the protocol has no knowledge of that, right, of the gas payment, right, because these are just smart contracts. Okay, so I abstracted away some things. So when a message is first sent to Axelar, before being passed to the router, it has to be verified. And verification is a crucial component of cross-chain messaging. That's what makes it secure. This is the security aspect of it. So how does this work? So verification is totally modular and programmable. Any chain connected to Axelar can verify messages however is natural for them, right? Whoever is doing the integration like can define it in the way that they think is most secure. It can also be changed, upgraded, etc. But this is a very typical example. We call this voting verification. We use this in practice a lot. It works very well. It's not perfect, but it's a very, very useful verification method. So what happens is the relayer hears an event emitted on the gateway that a message was supposed to, a cross-chain message is being sent, it relays it, and the source gateway on Axelar has an associated verifier contract for itself, like it's its own verifier, it's not shared, and it asks, like, please verify this message. What happens then is then there's these off-chain verifiers, these proof-of-stake entities that hear that there's a message that needs to be verified, and what they do is they look at the message and then they basically look up that message on the external chain, on the source chain, and they check, is everything exactly as the relayer said? Are the contents the same? Is the payload the same? Is the destination the same? Is it exactly as it's said? And if it is, they vote. They vote and they say, yes, this message is valid and ready to be routed. Once the message receives quorum, right, and quorum is very high in these cases, it's usually 80–90%, then the message can be routed. If it never achieves quorum, it can't be routed. It'll just be dropped on the floor, right? So this is voting verification, and this is one of the most common verification methods we use at Axelar, but it's not the only one. So another verification method that we use sometimes and is always possible is called light client verification. Some of you might not know what a light client is, but a light client is basically when a smart contract on another chain, like say on Axelar, can verify the authentic, like what happened on a source chain by just like checking the validator signatures. You can pass it basically in the XRP Ledger example, you could pass it a ledger header, the validator signatures, it would need to know the UNL in some way, and then it can just, in a Merkle inclusion root or inclusion proof, and then can verify like this transaction occurred. It can like sort of understand the other chain, at least enough to verify some transaction occurred. IBC is a light client, right? It's the most common. So you can decide to implement your verifier as a light client. So this is why Axelar is programmable, that it's not, like you don't have to do the verification in some specific way. It doesn't have to be light client, it doesn't have to be voting verifier, it can be something else you came up with, right? And it's changeable, it's upgradable. If you decide, oh, I found some issue with this, I'll upgrade it. Oh, the research happened and I like think that there's a better way to do this, like upgrade it, right? You're not stuck in one way. This is just for illustrating the example. Like you could put both of these together, right? Where you have a light client verifier and a voting verifier working together. So you receive a message and you need both those methods to say yes before you route the message. I personally think this bridge, we haven't built this, but it's totally possible. I personally think this bridge is the strongest bridge you could ever build, right? Because what happens is light clients are very, very strong, but they have bugs sometimes, right? But the Binance bridge hack was a light client and it was a bug. It's like $500 million lost, right? It's a problem. Usually they're very good, but sometimes they have bugs. Whereas voting almost never has bugs. But the issue with voting is, technically you could corrupt these verifiers and get them to collude and vote on transactions that are not valid. But the light client would reject that. So like the likelihood of the light client having a bug at the same time the verifiers decide to collude is like so minuscule, right? So you could do this, right? And you could add another one. You could add 3 verification methods and say, I need 2 out of 3 before it's routed, right? The possibilities are sort of endless here with this. So yeah, this is what I've been talking about, is modular verification. You can do a ZK proof in here, you can plug it in. Doesn't matter, the protocol is totally agnostic to that. The verification methods need to be approved via governance. So like if you write some verifier that's very, very bad, like assume it won't be approved via governance. They can also be upgradable via governance as well. And when I say governance, that's the Axelar validators, like the Tendermint validators of the Cosmos chain itself. They, like, anyone can submit a proposal and say, I want to upgrade my verifier, and if it's voted yes, in about a week, it goes live. So proving, this is the other side of the flow. This is like messages coming, like leaving Axelar. How is this done? This is just the reverse of verification, basically. And again, this is also modular, but this is one example. This is what we usually do. When the destination contracts on Axelar receive a message, say like I have a message for your chain, they basically construct a proof. They put the messages in a batch, and then they have the verifiers that are off-chain. These are the same verifiers. They sign the proof. And then that signed proof can be passed to the external gateway, and the external gateway knows who the verifier should be, and it can, then it says, okay, these messages can be executed. So that's proving. These verifiers here, these are specific to the connection, so this is not necessarily the same set of verifiers on the source chain. Like each connection has like their own verifiers, though there will be overlap. So yeah, I just said this is modular. Proving is modular as well, right? If you want to do ZK stuff, like something different, you don't like whatever the standard prover, you can have your own prover. So the required components for integration. So we write a bunch of core smart contracts, but then any chain that wants to integrate needs to implement a couple things. And for the XRPL integration, this is being done by Common Prefix, right? And they've done a great job. But so you have to write a couple smart contracts. So we have a gateway, which is sort of what receives the messages, a verifier, which verifies incoming messages, like messages from your chain to Axelar, and a prover, which is to Axelar, or from Axelar to your chain. Right, so you have to write those three components. You need to write a relayer, but a lot of times you could just reuse the existing relayer. It's pretty simple. And then you usually need some off-chain stuff, like the code the verifiers run to vote. So it's usually just things like how does someone look up a transaction via RPC on my chain, right? You need to write that in the off-chain verifier. So these are the things that you need to integrate. Once you have these, like you can integrate with the Axelar network. I'm going to skip this slide. So how do we pull this off, right? I always, after a while, this was like a little mind-blowing to me to understand, like, there's no real set verification method for Axelar. Like, it doesn't have to work a certain way. Like, everything downstream of the router has no knowledge of your verification method. So like the external chain, the dApp, the gateway, like where you're sending it to, they don't know. Like if you're running a light client, a ZK proof, voting verifier, if you change it, they don't know. It doesn't break anything. Nothing breaks. Like anything you do on your verifier contract is just abstracted away from the point of view of the router. If you get approved by governance and get plugged in, like that's it. That's like all that you really need to do. But it's not like the light client proof is passed all the way to the destination chain, or that packets look different if you change your verification method. They're always the same, right? So that's why we say this is programmable. That as you program over there on the left side of the screen with your verifier contract, like you have unlimited freedom to program this how you want, right? It just needs to be approved by governance to be secure, but you could do whatever you want. It's very, very flexible, and the messages still look the same downstream from there. So I think this is like very, very powerful. Like you can even integrate Web 2 systems like this. Like it doesn't have to be a chain. It could be anything on the other side there, and you pass it through the Axelar network to blockchains. Okay, this is the standard packet structure. This is basically all that's enforced. There's a couple other things that are enforced, but every message coming through has to look like this. So it's where it came from, source chain, source address, where it's going, destination chain, destination address, the data, that's a payload hash. We pass hashes so that way you don't need really large packets flowing through the network. And then an ID. ID is important, and we impose some structure on that because the ID is how the external chain ensures only once execution. So you need to make sure like a given message only has one ID. So even though it's string here, there's like some internal structure and a little bit like some security around that. But this is the standard packet. So no matter what your verification method is, as long as you get to this packet, you could pass it through the Axelar network. If you're a Web 2 system, put it in this packet. format, right? And on the other side, that's what you're going to receive. So yeah, so tokens are just sort of like encoded into this packet format, right? A bridge is just a smart contract, and it generates some payload and ends up with the same packet format. It's just, what is that payload? That payload says, this token was sent to the gateway with this amount, and that tells the other side, like, lock, unlock, burn, mint, whatever, right? So there's not like tokens have no special place at the protocol layer. It's just messages, and the tokens are built on top of that. And Axelar provides smart contracts and a product called Chain Token Service to make that really easy, so you don't need to write your own smart contracts for that. You can just clone our contracts, deploy them. You can even do it through a web interface, actually, without even having to write the smart contracts. So now, with the remaining time, I'm going to talk about the XRP Ledger integration. So XRP Ledger has no smart contracts, right? So the gateway is just a multi-sig account, right? And the signer set of that multi-sig account is the verifiers on Axelar, the people that have staked on Axelar and are authorized by governance, etc. And they control a multi-sig account on XRP Ledger. And this is kept up to date as it changes. And basically, the user will send a payment transaction to the multi-sig account, and that's just treated as the gateway and picked up and relayed through the Axelar network. And then coming to XRP Ledger, the multi-sig account sends payment transactions to the user. This is the packet structure coming out of XRP Ledger. So we put the data, the cross-chain data, in the memo here. So this is JavaScript. So basically, for the memo, each memo type, that's basically the field name. So you got destination address encoded as hex, destination chain encoded as hex, payload hash encoded as hex, and then the data itself. Here's the payload hash. It's going to Ethereum, and there's the contract that it's going to on Ethereum. And then you have the token up there that you send. You'd also specify the gas payment in here as well. I omitted that for simplicity, but you would put gas in here as well. So you send this to the gateway. The relayer hears it. It sees there's a transaction that was sent to the Axelar gateway with these memo fields. It translates it to the standard Axelar packet structure, passes it to the gateway on Axelar, the XRPL gateway on Axelar. That needs to be verified. This is the same voting verification. Well, today, the way it's going to be implemented is the voting verification that I explained before. So these verifiers, these are staked on Axelar. They run Ripple D nodes. They verify the gateway transaction. They see the hash. They check the memos. Is everything exactly as it said? If it is, they vote yes. If it isn't, they vote no. And then it's routed if it was verified correctly. Proving, this one's kind of complicated, but interesting. So what happens here is when a message is going to XRP Ledger, there's this prover contract on Axelar that gets the message and creates a payment transaction on chain. So it knows the XRP Ledger serialization format and creates a payment transaction that's going to be sent from the multi-sig gateway. The verifiers then sign that payment transaction. They send their signatures on chain. The signatures are aggregated on chain. When it's ready, an event is emitted, and the relayer picks it up and submits it to the multi-sig gateway. So this is a payment transaction signed by those verifiers that control this gateway, and then the payment is sent to the user, basically. Yeah, and so this is talking about how the verifier set is kept up to date. So if this verifier set starts to change, new verifiers come in or verifiers leave, basically the prover can detect that. It queries, it knows what the new set is supposed to be. It creates another signerless. It creates a signerless set transaction with the new set. The current verifiers sign that, so it's like a handover process. That's relayed to the gateway, and then after it's relayed, the gateway now is accepting signatures from the new signer set, or the new verifier set. So all this, again, is programmable, right? I've always wanted to build a light client for XRP Ledger because I think it's simple. All you need to do is make sure that verifier contract knows the UNL, right? That's the main hard part, is how do I give it the UNL? Maybe proof of stake voting on the UNL, right? There's a lot of possibilities. Or you could have both of them. You could have a light client and the verifiers. You could do something else, right? So it's totally programmable. So the XRP Ledger community doesn't like some specific thing about the way messages are verified or approved. It can be changed very easily without changing anything downstream, without any dApps breaking, without users even knowing. Right? That's what it really means to be programmable. So yeah, is there any questions? Yeah.
Hey, CJ, can you maybe help us understand a little better? Let's say that I sent a message from XRPL onto another chain, then it'll reach the gateway on some other chain, right? So what, I guess, permissions does the Axelar contract on the destination chain have? So let's say I say, that I'm sending 100 XRP. Does that contract have the ability to perform a user or call another smart contract on the EVM on behalf of an XRPL user?
The smart contracts need to be integrated. They need to implement a certain interface. They need to know the gateway on Axelar, right? And so they are not executing as another user. They are always executing as themselves if they need to execute. But you basically inside this execute function, you as the dApp developer implement this execute function, and you see the user is the source address, right? Axelar passes you this is who the user is supposed to be, right? So Axelar you can't really call Uniswap natively through Axelar if Uniswap is not integrated with Axelar in some way. You could maybe write some fancy proxy to do it, but the dApps need to implement some interface to receive cross-chain calls, if that makes sense. They have to implement this interface actually here. Yeah. Any other questions? Question back there?
Yeah, question. Well, I have a loud voice, so it's no problem.
Okay.
It's a twofold question. One is on the lines of voting. So if you're relying on vote-based relayer, it means that I have to trust those verifiers that are voting. Why should I trust those verifiers? That's question one.
Yeah.
And question two is, how do you deal with verifier availability? So let's say your verifiers go down, nobody can vote, what happens then?
Yeah, so first question, why should you trust the verifiers? These verifiers are verified via proof of stake, they lock up a significant amount of Axel token, or it could be a different token. They're also authorized via governance, not anyone can just come in with a bunch of money and become a verifier, and there's a lot of them, right? Decentralization is really the strongest property here I've found, in practice, the ability to, once you have 50 or 75 verifiers, the chances that they will collude is just so slim, right? So that's really the key property. Verifiers also get rewards for verifying these transactions. So if they start behaving malicious, they get their stake slashed, they don't give rewards, right? They are probably verifying other chains, and they'll get kicked out of all of them, won't get the rewards for them, get their stake slashed for them. Usually they're also known entities. It's a company or something, reputational risk, right? That's the whole thing. So, yeah. What was your second question?
You answered it already in terms of verifier availability, but you said big numbers, so.
Yeah. For availability, yeah, big number is the thing, and they don't give rewards, and eventually they get kicked out. Governance can kick them out for not voting, right? Because liveness is obviously a big issue and important. So, yeah, go ahead.
Yeah. How do you prevent spamming of relay messages on the network?
A valid message or an invalid message?
Invalid messages.
That's a good question. So there's a couple things that are done about that. So relayers usually only relay messages that gas is paid for. So you charge a decent amount of gas up front to make sure that you don't get hit with spam, because otherwise people will spam it. And you can also, you can refund people if they pay too much gas. We also charge a decent amount of gas for the method calls that do the routing on the Axelar network. We add a little bit extra just to make sure people don't spam it. So those are the things. But there's also other optimizations that we do. The verifiers here, they can sort of understand if spam is happening. If they get a bunch of messages that are just are not found, right? They could just drop them. They don't really have to vote. You could just refuse to vote, and then it's just dropped. So those are the main ways. Any other questions? all right, I'm pretty much done. I'll just wrap up. That's really it. This is our repo. If you want to take another look at it, right, this has documentation, all the stuff, and the code that we built, all the smart contracts, and talks about how to integrate and all the stuff I talked about today. So thank you very much.